अहिले यो हामी युट्युब च्यानलबाट पनि लाइभको लागि प्रिपेयर हुँदैछौँ। केही मिनटमा केही सेकेन्डमा लाइभ जान्छ यो। जस्ट सेटअप हुँदैछ। Thank you very much for joining us today. So we are live on YouTube. So those who have issues joining us this session, you can join us from YouTube as well. And those who are joining for webinar session here on Zoom platform, you can put your queries with your association and so you can ask your questions in Q&A section, and likewise you can post your questions in YouTube channel if you're watching from us in YouTube. So when you ask questions, please make sure about your association, your academic qualifications, or which help us to respond to you quickly. So with this special note, I would like to welcome our special guest, our speaker today, Professor Dr. Binil Arialsa. So he'll be sharing with us about how we can study astrophysics. Probably many of you haven't thought about that you can actually study astrophysics in Nepal, and you can do research on it. And it's not that recently; it's been a decade. So it's been a long time. There has been a lot of research works carried out in a different stream of astronomy and different domains. So Sir will be explaining more about it. And let's welcome Sir to this webinar session today. Welcome to the program, sir.
Thank you. May I share my slide?
So we can see that.
Okay. First of all, I would like to thank organizer NASO for arranging this very timely, because we are locked inside the home. What we can do from the home in this particular field, I will also explain this. Thanks a lot, and NASO. And thank you very much for coming, for attending today in the morning. So I will go through my slide. As you know, today we are going to discuss about how to study as well as how to conduct research in astronomy and astrophysics. Before starting the talk, I would like to introduce myself, what I did in a couple of slides. I did PhD from Innsbruck University, Austria, in the year, I started it in the year 1998 and completed in the year 2002. So he's my supervisor, Professor Dr. Walter Sauer. He's working, he's very actively working there as a professor and as a team leader of Institute of Astrophysics in Innsbruck University, Austria. I completed my PhD in the field of galaxy orientation. I will talk about this a little bit later. I trained from this observatory, Asiago Observatory, which was very close to our institute. It's only 240 kilometers far from my place. So I repeatedly visited this telescope. This is 2.4 meter optical telescope. I trained. I spent quite a lot night, more than 52 nights observing night. And a few data I have used, I collected myself and I have used for my PhD. Later, in the year 2001, I got an opportunity to spend about 50 observing nights in this very good, very well-known telescope named Galileo telescope, which is at Tenerife. It's an island of Spain, belongs to Spain. So most of my work, my data that I have used for my PhD is from this telescope. And after analyzing this data, I'll go through how I analyzed or how one can analyze later. After analyzing data critically, we were able to publish this paper immediately. In this paper, this was published as a letter to the editor. We found some misinterpretation regarding this particular area, misinterpretation in the methods. So we proposed a new method while analyzing, say, distribution of angular momentum of galaxies. You probably know what is angular momentum and what is linear momentum. And after completing PhD, I got opportunity to work on this Cosmo telescope as well. This is sub-millimeter telescope. This is very important telescope. Through this telescope, we can study star formation activity. There are a few issues. Still, those issues are not solved in the case of star formation. So they are looking to solve. They are trying best to solve those issues. I spent here, and then I moved to University of Washington, Seattle in the year 2002. I completed PhD and learned something from Cosma as a research assistant, and then I got postdoc position in this University of Washington. And I spent 2.5 years in this university, University of Washington, Seattle. During those periods, I got a rare opportunity to frequently go to the Mauna Kea Observatory. I was the first Nepalese till that time who visited Keck Observatory. Keck Observatory is one of the largest optical telescope, as well as it also covers some region of the infrared wavelengths. So I learned a lot. I learned a lot of things during my stay in University of Washington, Seattle, as well as this very well facilitated series of observatories, range from, let's say, infrared to ultraviolet, I should say, up to some portion of ultraviolet, because you know ultraviolet is blocked by atmosphere, most of the portion. Okay. And during my postdoc, I also visited a few nights in Alma, Chile. I was there for 4 nights only. So this is a radio telescope. You can see area of telescopes here. You see the size of the vehicle is here. So this is a very important, very active radio telescope. Still, lots of new interesting projects are going on through this ambitious project. After completing postdoc, I come back to Nepal after I spent about 8 years in Austria and in the United States, and I returned back to Nepal and joined Tribhuvan University as a lecturer of physics. I do physics in my department. Now I am head of the department. My responsibility is to look after physics curriculum of Tribhuvan University throughout the nation, from graduate level to postgraduate level, as well as research activities as well, broadly in physics. But personally, I do research work in astrophysics. I teach astrophysics. Okay, now I move. This is just to introduce myself and my journey, my professional journey to astrophysics from abroad to Nepal. So just look at the fundamentals. Astrophysics, if you look at the astrophysics and its research area, you can classify astrophysics into 4 different disciplines right now. First, very sophisticated, this is astroparticle physics. And second, I should say this is new and this is very challenging, and lots of genius people are working in this area, particularly in the United States and in Western Europe, experimental astrophysics. This is these people perform astrophysical experiment in the lab. These people do not observe, do not use observatories, create the processes that occur in the nature, that occur inside the stars, or say inside other celestial objects or in between the objects. And many fascinating experimental plans are going on. And this is a very old domain. You all know, after Galileo, we are used to see sky through some tools, through some, say, handy tools in the beginning, and later we have a very sophisticated tools installed in space as well as in ground. So this is a very traditional, as well as lots of things we know because of the observational astrophysics. And this part is always very important, theoretical astrophysics. This part obviously use mathematics and cosmology rigorously to predict some theoretical model, and so that these people can verify these models. Okay. So first of all, I would like to explain this observational astrophysics. This is a very broad area. Not only physicists, also mathematicians, engineers, technicians work in this particular area. Now, there are many space telescopes, but I should focus on only 35 space telescopes and 40 ground-based telescopes. They are doing very amazing work, also providing data to the students of underdeveloped countries. So this includes space telescope as well as ground-based telescopes. You see, secondary data is available for research. I will show you how you can get data and what sort of things you can do with the help of those data. You see, the expenses of this project is very, you see, $700 trillion they have spent. But we don't need to pay even a cent to get a data. So data is freely available. Even primary data can be available if you have a collaboration with other research projects. If you have a collaboration, you can get primary data. You can analyze primary data. Secondary data is also extremely important, because there are lots of things we don't know. We need to analyze very critically. We need to perform. You need to think on our own hypothesis. I will go through this. This astroparticle physics is very sophisticated. So from Nepal, even with the help of collaboration, it is very difficult to perform, difficult to work on the project based on astroparticle physics, because we have two problems. One is we don't have very high speed computing facility here. We don't have dedicated internet facility here. We have normal internet facility here. So we cannot manage the data, very large data that cannot be put in the Excel pages, very large data. You have to work with the algorithm to manage data. You should know the data science to manage those data. And so this is, you can have exposure to this, but right now I should say this is not very easy to do something in astroparticle physics. Even though a couple of mine students, they have carried out master's thesis under my supervision in this particular area by collaborating with the people. They are in Geneva, in CERN, CERN, LSC, Large Hadron Collider. But this is difficult. This is more difficult, because only high rank universities, up to 20 or 25 ranked university, they have this sort of very sophisticated experimental skill to create sky in the lab. So this is also very new area. I think only 15 to 20 years, if you look at the age of this evolution of this particular experimental stuff in astrophysics. This is very famous, and we are rich about this. We have several telescopes ranging from radio to gamma rays to observe sky through electromagnetic radiation of different wavelengths. So you know this, and this part is always important. But luckily, we have a thousand and thousand of theoretical models that needs to be verified through experiments, because science is, after all, experimental in nature. Whatever we think, we should verify through the experiment repeatedly, unconditionally. Now I just want to give some exposure to what sort of work they are doing in these domains. In this astroparticle physics, they are looking for, physicists are, or say the scientists are looking for some unknown problems, unsolved issues that can be, say, the baryon asymmetry, probably baryon and leptons. There is a principle proposed by Sakharov regarding the baryon asymmetry problem. How first proton form? How there was only energy in the beginning, it is believed that. So first proton formed because of this baryon asymmetry, and we don't know exactly the details of this baryon asymmetry. And monopole problem still exists, because what our physics used to claim or used to advocate is there should be magnetic monopole somewhere in the universe, but we haven't detected magnetic monopole till date. So to have a magnetic lines of force, magnetic field, there should be a magnetic dipole. And something about the details of this GUT, you probably this grand unified theory. So this is important, quantum chromodynamics, to understand this. Also the Higgs mechanism, probably you are familiar with this Higgs, this word. We discovered, or physicists or experimentalists discovered Higgs particle, but they don't know how Higgs mechanism occurs. so that the fundamental particle got their fundamental properties. For example, we know electrons. We also know the mass of the electron. Mass of the electron is 9.1 into 10 to the power 10 to the power minus 31 kg. And you know the charge of the electron. So, but you don't know, or we don't know exactly how these charge and masses are distributed within the electron. Till date, we don't know distribution profile of the mass and charge of fundamental particle. So why mass of electron is this much and mass of proton is this much? So this mechanism, Higgs mechanism, is responsible to give mass to the protons, mass to the neutron, uh, and other properties to fundamental particles. So, experimentalists, they are trying to perform those mechanisms through which we can understand the distribution profile of charge, mass, and also the intrinsic other intrinsic properties, including magnetic moment, uh, intrinsic angular momentum, and so on. So these are the very fundamental issues related to fundamental particles and the behavior of those particles. So these works are going on in these projects. Experimental astrophysics is also very fascinating. People are doing underground experiment as well. Gran Sasso is in Italy, and also Sudbury. This is in Canada. They are looking for many other problems related to neutrino. You know, neutrino is also fundamental particle. Probably some of you are not following me. I will come to next slide and I will begin from the very beginning. What sort of physics you need to study to perform research work. Okay, this is just the aims of this project. These are unsolved issues. You know, gravity is the oldest force. There are 4 forces in the universe, you know this. But gravity, among them, gravity is the oldest force, but that force is least known force. We don't know how gravity behaves. What is the origin of gravity? There are several issues regarding gravity waves. Gravity is not at quantized also. There are several other problems related to dark matter and oscillation of this very important personality disordered properties. This also exists. If you probably those of you who are studying BSc in third year probably, or in fourth year, you study this CP problem. C refers to charge conjugation and P is for parity. This is strong CP problem. So these are the problems. And so they are looking to solve these problems. With the help of observational astronomy, these works should be done. These unsolved issues should be understood within a few years or within 10 years or so. There is a problem regarding black hole. Recently, we hear news about the probing of black holes. So we should know some other properties of black hole. Particularly, we should go up to the event horizon and look at experimental data when particle just infalls inside the black hole. Just before infalling, we should get data within 5 years or 10 years, we hope. And there are several issues regarding gravity waves and observational astrophysics as well as experimental astrophysics. They are also, both are looking for gravity waves, details of the gravity waves. Regarding theoretical astrophysics, we have a very well-established theories. String theory, probably you know, M theory, you know several issues in this GTR. This is general theory of relativity, and this is you see, GTR is not compatible with quantum mechanics, but this is very successful theory. These are the problems, or say these are the issues in which theoretical astrophysicists are looking for. But this reason is almost solved. There are many people, including mathematicians and so on, cosmologists as well. So here we have to probably in the coming 20 years, more genius people and more young people will involve in this area. Also in this area, high-skilled people, manpower, particularly high-skilled computational skill, as well as the detection, planning skill, planning for the experiments, those people are needed also here. Okay. Now, what sort of knowledge we need to understand to go in this discipline? You need this QFT. You have to go through the details of quantum field theory. Without understanding quantum field theory, you can't go to the high energy physics or high energy. And if you don't have understanding of high energy physics, you can't go through the astroparticle physics. Okay, so, and also I have written FD calculation. This is actually Feynman diagram calculation. This is regarding the interaction of fundamental particles and also composite particles. And a huge data is there. So you have to go through the algorithm of data science, and you should have a very high speed computing facility with dedicated internet facility to handle this area. So what we have in Nepal, you can study quantum field theory, just the fundamentals of quantum field theory. You study only 3 credit hour quantum field theory. If you do MSc Physics in Nepal, in Trivandrum University, regarding Feynman diagram calculation, you will be exposed with the Feynman diagram calculation during your MSc. So you will study these two a little bit, not all, not sufficient. These are just the fundamentals, 3 and 3 credit hour course. So to know to know more about quantum field theory, you should take at least 9 credit hour course. So probably you should go to the other university in Europe or United States to complete QFT necessary for astroparticle physics stuff. This is similar to this Feynman diagram calculation as well, also because this calculation also use QFT. And regarding data science, we don't have any facility here. We don't have curriculum in TU, in KU, or in other universities. But a few department or few institutes are trying to do something with the data science. Probably in the future, we'll have a department or courses regarding data science, either in mathematics department or in statistics department, or probably in physics department. I can't say right now. To go through the details of experimental astrophysics, you have thorough knowledge of these two. Quantum chromodynamics. This quantum chromodynamics deals the interaction between quarks as well as composite quarks to form a neutral hadron or meson or baryon or whatever. And this is also extremely important to understand, because a large number of experiments are planning this particular, using this particular quantum fluorodynamics. And this is for the flavor charge quantum mechanics. This is for, particularly, this is for strong force. This is for weak force plus strong force. So this is highly energetic. This is relatively less energetic experiment we can perform. Also, those experiments are also performed in this LHC, Large Hadron Collider. And in addition to these two, you should have some skill regarding engineering of detector. Detector technology is very important for this domain. Also, this domain requires badly artificial intelligence. AI is needed for this domain. So this is a relatively very challenging and very fascinating area. Probably we'll explore in the future. You will study a little bit QCD if you study here MSc Physics. QFD, we have no content in our curriculum. In Nepal, detector technology, nothing. And artificial intelligence, regarding this, in Engineering Institute of Engineering, TU, as well as in Pokhara University, they have curriculum regarding this. So there is a little scope of understand, go through the this AI. Observational astrophysics, for this area, you have studied or you will study in Nepal as well as in other nations. You need classical physics. You have to understand classical physics. You should have handy with mathematics. You should have a concepts of mathematics. You should go through the statistical tool, and a little bit non-reductive quantum mechanics is also needed to handle observational astrophysics. So you have studied or you are going to study during your BSc, lots of quantum mechanics, also mathematics. You have studied lots of mathematics if you are in physical group. Also, probably if you have choose to statistics, you are familiar with lots of strategy. This is sufficient. And also in master's level as well as in bachelor level, you have scope of learning this quantum mechanics, particularly non-reductive quantum mechanics, not quantum field theory. So you can go through the details of, go through the problems of observational astrophysics, and you can handle because you have a theoretical background. And but that this background is should be very sound. You should go through the details of these things. I will explore this in next slide little bit more regarding theoretical physics. This is not easy. You see, you have to understand at least general theory of relativity. We have introduced general theory of relativity in this MSc Physics semester system course recently, and cosmology is still not compulsory. It is an optional course, and mathematics you have sound knowledge with mathematics. If you do BSc physics, this is sufficient. But lack of GTR, it's difficult to do. But if you are interested, if you do yourself, if you made a group, if you learn from each other, if you contact a teacher, you can do anything. Except I think this part is very handy, and you need skill also, not only the knowledge. Also, this part is even knowledge will work in this part, but here you need skill much more than knowledge, and you see, understanding of those knowledge. Skill and invention is very important for this. Now, this. I just want to repeat for myself, I should say. This. There is no separate institute for astronomy and astrophysics in Nepal. Means in Trivandrum University, in Kathmandu University, or in other university, or in say separate institution, there is no separate institute or department for astronomy and astrophysics in Nepal. Okay, there is a department of physics. So in my department, all other disciplinary people are there. So also the astrophysics who do astrophysics are working in my department. This is one thing. We don't have separate institute. We don't have separate funding for astrophysics. Only TU, Trivandrum University, offers astrophysics course at master's level. Only at master's level. This is also compulsory. This is also elective course, not compulsory course. So there are altogether 12 credit hour course. 4 courses are there. This is the data of Central Department of Physics. Till date, 220 students completed a master's dissertation, means research work in astronomy and astrophysics from Central Department of Physics, Trivandrum University, and 3 PhD have been awarded in astronomy and astrophysics from Central Department of Physics, TU. These are the outcomes. So most of the students are right now in the United States. They are doing PhD and postdoc. About 60 completed PhD, and they are some of PhDs are faculties, and some are doing postdoc in the United States, and also in European nations. A few are in European nations. Okay, so to do research in astrophysics, you need to have a very good knowledge of fundamental physics. You need to understand theory regarding electromagnetic waves, because what we are going to analyze is the data that we obtain from telescopes, and those data are electromagnetic waves. Data comes from the electromagnetic waves. We look at the sky and we collect electromagnetic waves. So our astronomy is completely dependent on electromagnetic wave. But there are also another astronomy. You see, gravitational wave astronomy is emerging since last couple of years. Even cosmic rays astronomy is there, but but these areas have a they are very limited because of the very sophisticated. They need very sophisticated equipment. So the astronomy is badly dominated by electromagnetic domain. So you need to understand electromagnetic wave propagation theory. You need to understand what will happen if electromagnetic theory passes through the metals, passes through the semi-metals, passes through the vacuum, passes through the gaseous medium, what sort of interaction they perform, as well as this process is a radiative process, the support radiative process. You have to understand radiative processes, all kinds of radiative processes that occurs in the sky. Those processes are very wide. You see, there are very hot objects in the sky and very cold objects as well in the sky. So these are how radiation emitted from these objects interacts and form a radiation field within the medium. And this is very important. So you should go through the details of electromagnetic wave stuff. And this is very important because you see, we have celestial objects. We have a planet, star, and the gases and dust and other particles in the sky. So we have particles. That why you should study particle physics, means the classical physics. They behave. So you need lots of classical physics, a little bit quantum mechanics as well. If you probe to the very energetic section, you need quantum mechanics as well. This is all the time important because this is a very handy, very important tool to handle with the large number of particles. If you have a large number of particles in certain radiation field, you have to choose your very strong tool, as well as many tools that you have studied in math physics. I have just written as an example, if you have a spectra taken by a telescope focusing a star, suppose, then you need to perform this Fourier transform process so that you can know what sort of spectra is there. You have to remove background noise. You have to remove foreground noise. You have to make that spectra in a standard form. You have to write a spectra. You have to write functions of that spectra, and you have to develop a theory of those thousand spectra. You have to generalize those spectra emitted from particular type of object if you do spectrometry. I have written three things here again. Not only those physics. The physics is not only the component to perform research work. You have a very good understanding of algebra. Means you should know what is the meaning of, say, a plus b whole square equals to a square plus twice a plus b square. What is the meaning of twice ab? You should know, because you know this, a plus b whole square equals to a square plus ab plus ba plus b square. Okay, if you assume AB equals to BA, then you can write twice AB. Okay, so what is AB and what is the difference between AB and BA? So because you don't know what is A and B, if you define particular parameter as A and B, then the situation will be changed. So you have to understand with the language of algebra. For example, what is the meaning of second order polynomial? What is the meaning of third order polynomial? What is the meaning of, say, Gaussian distribution? What is its equations? and what is the meaning of other normal standard distribution or other distributions. Okay, so what is also the other functions, say trigonometric function, hyperbolic functions, you need to understand, because you are going to put trigonometric function within the algebra. You are going to put hyperbolic function in the algebra. Also the exponential function. Exponential function can be growing type or decaying type. You have also other types of functions. You see, functions is very important. You know, what is function? Function preserves the structure of the system. Function preserves very well. So function is some sort of isomorphism. It's a very beautiful thing. Okay, you are going to use function within this. You are going to analyze data or predict something new if you perform research. This is all the time important to handle data. And also these days, these things, whether you do algebra or whether you put your hypothesis in the form of some equations and you handle the data and try to test those data for your hypothesis for that equation, you should have a computational skill. So we perform virtual experiment in the using the real data. So this is based on your hypothesis. So you need to identify your research interest. So first of all, these are the basis you need to perform research work in astronomy and astrophysics. You don't need to go through the details of quantum mechanics, many things about the quantum mechanics. But electromagnetic wave propagation, you need to study mechanics very well. Classical mechanics, means mechanics. You need to know about the mechanics, all kinds of mechanics that you have studied during BSc as well as during 11 and 12. And this is something probably you have studied a little bit during your BSc, you have to know, and lots of math, physics, and these things. I assume you are listening, isn't it? Okay. So I move to the I go to the how to create interest and how to compile data and how to put hypothesis to do something new from your home in astronomy and astrophysics. I have shown here 5 different database center. This first one is called ADS. This is very famous. This is maintained by Harvard University. This is free for all. I will also send this slide to you all, so you don't need to write down right now. So ADS is all the time important. And CDS, this is maintained by European Space Agency and managed by Strasbourg University, France. This is also extremely important database center. And NASA's database, obviously, this is also important, particularly for extragalactic sources. This is maintained by NASA. These are very big centers through which we can get literatures, millions of literatures, millions of data of millions of different objects covering all wavelengths. And this is also handy and important, particular for the countries like Nepal. This is also maintained by Strasbourg University. You get secondary data for photometry from the Skyview Virtual Observatory, and for literature, AstroPS or archive is always important. So first, I would like to go through ADS to show to show you how to extract data from this, or how to, first of all, you have to be motivated from something. So you have to go through the literatures or books or something, some triggering issue, so that you can be motivated. Okay. Go through this web page. This is ADS. You can, if you type this, you get a form like this. And here is several options. If you want to know something, for example, I have written, probably you know Hubble's law. You are familiar with Hubble. You have studied Hubble during your schooling. Okay. So if you want to know what Hubble did, what sort of paper Hubble published, how Hubble discovered Hubble's law. You can just use this and type your interest. You can type a name, say Hubble, or you can also type publication date. Also, you can also type the keywords. For example, if you want to study, if you are interested about pulsar, to study black hole, or to study active galactic nuclei, or anything that you want. Okay, I have just typed Hubble here, Hubble, comma, and put one space here and E. I have typed this. And I have also said this because in our book, even in your school's book, probably you know, during 1928, Hubble discovered his law. So I have just written 1927 to 1930, so that I can know how many papers he published during this period. January 1927 to December 1930. Okay, if you type this, and if you specify these two targets, and if you click here, submit your query, what you get is, you get a list of papers published by Hubble during those period. Just by looking the title, you see, these are the titles of those papers. Just by looking, you see here, number 4, a relation between distance and radial velocity among extragalactic nebulae. So you can jump to one of them. So in this paper, he published his law. That's why I made it for this paper. If you jump, you need to click here. So blue is active region. You can click blue wherever you want. You will get this description about that paper. Here you can see, you can download his paper. Here it is written, full refereed journal article PDF and PostScript file. So jump to click here and you get that historical paper. This is the paper published by Edwin Hubble in the year 1929. In this paper, he discovered, or he claimed, there is a relation between distance and radial velocity of galaxies. And he concluded that distant galaxies move faster than near galaxy. In this way, you can download or you can study almost 30 million literatures, review articles of, probably this is fascinating for you to study the papers of, to read out the paper of Einstein, Heisenberg, Pauli, Dirac, Bethe, etc., to even up to these days authors. Okay, so we should thank Harvard University for maintaining this huge data for all researchers as well as the students. Okay, now I again go back to that same query form. I typed my name here. Okay, Arial, comma, one space and B. So this data covers all literatures published in the international journals till date, not only of those prominent physicists. Okay, if you just only write my name here, you will get a list of papers published by our groups. You can jump to one paper, jump to one of them. For example, I just clicked here. Then you will get, if you want to read out the paper, you see, you can download the paper, full refereed journal article, PDF PostScript is available here. So if you click on that line, you get paper. You can download the paper. This is just the first page of that paper. So in this way, you can download, you can download many papers. In this way, you can download paper just by typing keywords as well, not only the name of the authors. Because you probably don't know who people are working in particular areas. So you have to create your own interest. Suppose you have created your interest, you want to know about what is pulsar or what is black hole or what is, say, gravity waves or anything. You can type your keywords, say pulsar, in two places, either in this publication date here or in here. Okay, sorry, either in this title words here and or abstract word here. This arrow is wrongly placed there. If you type, I have typed pulsars just to show you. To make it interactive, I avoided internet connection. I just put everything in my slide to save time. Okay, so I typed pulsars here. That's all. And I send it as a query, you will get a large number of paper if you type only pulsar. You see, you get this is retrieved 200 abstracts starting from number 1. The total number selected is 19,572. So there are more than 19,000 papers related to pulsars. So what I suggest is you should try to read review articles, review papers in the beginning, because research articles are difficult to understand for the beginners. First, you have to go through your books to understand fundamental things that I have mentioned in previous slide. Then you can go through the review papers in your particular interest area. Okay, so I have just written just this is home because we are we are locked inside the home. So you can do several types of research works using different wavelengths. With the help of radio wavelengths, science, what sort of science can be done with the help of radio wavelengths? What sort of science can be done? New science can be done with the help of sub-millimeter wavelengths or sub-millimeter astronomy, infrared astronomy, optical astronomy, X-ray and gamma ray astronomy, even cosmic ray astronomy. So each wavelength has their specific importance. So these are the issues now. There are several issues regarding galaxy rotation curve of galaxies. And this issue is, people are trying to solve this issue using radio wavelength. I have just written, there are many dark, if you want to do something dark matter, something with dark matter, this is macho type dark matter, not the axions. You have to go through the radio telescopes. Within radio telescope, there are also several wavelengths, near radio telescopes and far radio band, near radio band. Two band is different from each other. Their science is also different. Similarly, I have written something. This is photodissociation region. This is very important region to form star burst properties. Star formation. There are several issues regarding star formation still unsolved. So you have to understand what sort of those discussions are still unsolved. Infrared astronomy is all the time very important. We have a more infrared telescope. If you compare the number of telescopes with other radio, sub-millimeter, optical, and X-ray, there are many infrared telescopes. There is a reason behind this very wide varieties of telescopes covering near infrared, far infrared. It covers interaction between the interstellar medium or even the extragalactic medium, particularly for small compounds, carbon and hydrogen, carbon and silicon compounds. We call it dust, and interaction between them. This is a historical area. Galileo started astronomy from using optical telescopes. So still there are many things that we need to know. So there are very important optical telescopes in the sky as well as in the ground. HST, Hubble Space Telescope, which is optical. Newton telescope, which is X-ray. Probably many, including IRAS, Akari telescopes, which is in the sky, and IRAM, that is 30-meter telescope, which is ground-based. So there are a few telescopes are in the sky, a few telescopes are in the ground to cover this infrared region. This region is very interesting. And sub-millimeter is also important. There are many telescopes. I should say these days, large number of people are working in this area. And the second one is radio telescope, and third is sub-millimeter. There are also many people. There are few people, but those people are very active and very well equipped. Those are working in X-rays. Okay, so what I suggest is first you try to create motivate towards anything, object or process. You can go through the black hole, or you can go through the processes to create black hole. Okay, so try to be precise and try to select one particular thing. And what I suggest is go through at least 10 important papers. Try to read out. Just read out. Try to just read out a paper, and you will understand only 10%. I know. Even I understand 20% if I read paper of other disciplines other than my own discipline. Say, I do not do say sub-millimeter. I haven't done anything regarding sub-millimeter. If I go to the literature of PDR, I will understand only 10%. Okay. If I do lots of infrared, also radio. If I read this paper, recently published paper that is on rotation curve, I may understand up to 40%, not 100%. To understand 100%, it's impossible. Only authors and their group, they can understand, because there are several technical issues behind the paper. So it's very difficult to understand their data processing way and other details regarding their models. In paper, usually people write only few sentences to reflect those things. So try to understand the methods. What I select 10 papers, or first try to go with one. And what you need to do is first read, do not read abstract. Do not read abstract. Go to the introduction section, read out introduction section, I should say 10 times. And if you do not understand particular words, try to go to the Google and try to understand the meaning of that particular word. Or go to the, you can go to the Wikipedia as well, but I do not recommend Wikipedia all the time. For in the very beginning, you can go to the Wikipedia. So go to the introduction section and go to the method section. You try to understand what sort of methods they have used to find their results. So this is very important, because you are planning to do something. So you should understand several methods so that you can imagine for your particular methods, for your particular problem. So go to the references of that paper as much as you can. So if you read out one paper, I should suggest at least you need to go to the 3 more papers belongs to that paper, references of that paper. And among 3 papers, 2 papers should be related to the methods. You can find many references within the paper regarding the methodology, regarding the, this is, I think, this is, in the beginning, this is difficult. So to make it easy, what I suggest to my student is, go to the, go to this personality. There are many, I think till date, there are 21 physicists or astrophysicists. They got Nobel Prize in physics and chemistry, 7 in chemistry, 21 plus 7, I should say. Because, you know, astrochemistry and astrobiology is also a part of astronomy. So what I do is I do astrophysics. Other people are doing astrochemistry. There is no people, only there is one guy who is trying to do something with astrochemistry recently in Nepal. Okay, so you can go through the details of these physicists or astrophysicists, how they perform their work, go through their development, academic development, achievements. This is very important. So at least these people, for example, here, Martin Rayleigh and Anthony Heavis, they discovered pulsar, on Nobel Prize, and stellar nucleosynthesis, probably you know, how star shines, how star emits electromagnetic radiation. This is because of stellar nucleosynthesis inside the star. So we should know about the stellar nucleosynthesis very well. And also the pulsar and CMBR, stellar and chemical evolution, and these things. These are also a few other astrophysicists with Nobel laureate. Now I go through the database, how we can get. I discuss a little bit about the literatures, how we can get literatures, and how to go through the literatures for making your research hypothesis. This is a very important database center. Now I moved to CDS. I had shown its web page before. I think it is perfect. Okay, I'll continue. Now I will take probably 20 minutes more, 15 to 20 minutes. If you go through the series, there is a large number of options regarding the database and the tools to handle those database, including free softwares and also the literatures, catalogs, and many more things. Okay. So you can get catalogs there. Also, the yellow pages, image atlas softwares are there. These are freely available for the students. Dictionary of nomenclature, this is also very important. AstroGlue, this is also important. Here is AstroWave. So these are the database. These will provide database as well as allo pages of database in which you can extract database as a whole in your Excel format or other format, whatever, which format you need, ASCII format or binary format. In Simbad, there are a very large number of database. I have written just one sentence here. The Simbad database contains information for more than 12.8 million astronomical objects, 12.8 million astronomical objects in all wavelengths, in almost all wavelengths. This is the web page. I'm sorry. So Simbad provides you a huge database of a very large number of astronomical objects in all wavelengths, in almost all wavelengths. This is very fascinating, very interesting. I just want to give you one exposure how to get data. This is a form. As I said before, this database is maintained by Strasbourg University through European Space Agency. So European nations funded this university, Strasbourg University, to maintain this huge database. This database connects more than 400 telescopes at a time. So real-time database is also available here. You can have a primary data access as well, but you need to collaborate with the other research groups who have access to uh, primary data. For example, I have 4 international projects for PhD work, and my 4 students, they are doing PhD in different aspects, and I have 4 collaborations, 3 collaborations with European Union. University belongs to European Union, and one is with National Science Foundation, which is in the United States. So they have agreed to access primary data, and I'm, as a collaborator, I am also involved in their projects. That's why I have also access to get primary data of my research interest. But to get those data, I have to apply my proposal, and I have to justify what sort of things I want to do with the help of that data, because primary data is primary data. You should have a knowledge to reduce that data appropriately to make it secondary, so that you can find something new using primary data, and and uh, and after that you can create several models. You can create, you should try to understand secondary data as well. Primary data usually gives you a direction of research area, or a specific path for a research area, and secondary data, with the help of secondary data, we can solve several issues, unsolved issues in astronomy and astrophysics. What I did is, I just want to give one just example. Uh, Here, if you type name of, I have typed the name of one galaxy. You see, Andromeda galaxy is our neighbor galaxy. You can type Andromeda here. This is Pinwheel galaxy, YM51. YM51. I have typed Miser 51. This is the name of the galaxy. If you go to the catalog of galaxies, you can find the name. Which one is our first neighbor, and neighbor, and so on. What I typed only YM51. This was default. I did nothing with these things. I typed here YM51 and just submit it. So you need to identify at least one object. You can type, here is an example. You can go through this, if you click it, then here is a very important information is there. How to write an identifier can be found in the dictionary. How to type, how this software will understand your object. Okay, so you can go through this, and if you submit it, what you get lots of information, including data, literatures, many spectra as well. So in the beginning, they will this software gives you a basic data. YM51 is C42 galaxy, and you can see the coordinates position of those galaxies. So if you know longitude and latitude, you know longitude and latitude of our Earth, but you have to understand longitude and latitude of our universe. There are several coordinate systems. We say it ICRC coordinate system or equatorial coordinate system, galactic coordinate system. You see galactic coordinates and supergalactic coordinate system. There are several coordinate systems. This is nothing. This is just the longitude and latitude defined for a specific purpose. This is the magnitude. Probably those who took space science course, they are familiar with what is magnitude, what is B magnitude and V magnitude, apparent and real magnitude. This is actually total luminosity of the star, morphology of luminosity of galaxy, obviously M51. Morphological type is there, and also the radial velocity. It means this galaxy is moving with 463 kilometer per second speed uh, uh, away from our system. This galaxy is moving. This is redshifted. That's why it is plus here. So this galaxy is moving far from us with this speed, 463 kilometer per second. Per second. In 1 second, 463 kilometer. So here you can see different identifiers. Means this object has been looked by several telescopes in the past, or still few telescopes are following this galaxy in real time. So these are the name of those projects, those galaxies, those missions. This is, we call cross identifier. This is basic data. This is called identifiers. So there are lots of missions. They are looking these galaxies, or they have already collected data of these galaxies for their interest, for their particular interest. If you scroll it down, you get plots and image tool, you get references. I have typed only 2001. Here you can see references from 1983 to 2000. I have typed within, I want to see how many papers are published within this period regarding this YUM51. I found there are 1,108 papers published, particularly on several aspects of YUM51 galaxy. Okay, links to images and field charts. This is bibliographical references. You can go through if you click it here, you can read out, you can download more than 1,000 papers written particularly on this object. These are for the measurements. You can get the data of these telescopes. They already looked, or they are looking, they are just focusing that M51 object. So measurements you can take, and there are also external archives, external links to get more things. If you go to this plots and image tools, you can download fits image or in different format of the image of that galaxies. You see, there are a fixed field. These are the fields of which data is available. You can also have the spectra of within spectra of this small field. You can get the data of spectra of small field. You can have an optical image using those tools. Those tools are available free. You can also download this and work during offline. And similarly, if you click on here to see the literatures, as I said, there are 1,108 literatures. You can go through the literature, you can download it as I shown before. This also linked with the ADS. So you get this from ADS. They are interlinked with each other. If we jump to one literature similar to the previous, you can have an abstract, you can download the paper. So these are CDS and ADS, they are interlinked with each other. And you will also have additional links. Similarly, regarding the data, if you jump to anyone, you get the data. You see, if you click on this, you will get the data. And there is also options regarding the downloading of that data, whether you want it in Excel format or in ASCII format or binary format or other format. It depends upon your operating system, what you have, what you are used to in your laptop or computer. Okay, so the spectrum of each pixel or each small field of view can be downloaded. Also, the data behind this spectrum can be downloaded. You can see the background level as well as the emission. You can perform, you can put hypothesis. And you know this, if you have wavelength along x-axis, and if there is a peak at particular wavelength, this means that this peak is because of some particular transition of particular element. You can identify element, which element is there in the galaxies in that particular region, why those elements are there, whether is it normal or is it abnormal. So you have to work on each field to get information based on your hypothesis. What you want, you should focus on that. This is just the format of database. You can also change your format. What sort of, how many columns you need to download data, what you put in, what you add in your first two columns and next two columns. There are some, this is very interactive. You can download as per your need. Okay. So I again back to the Simbad page. So in this way, Simbad, I sought Simbad because in Europe, what I found is even the school students are working research work, small work, project work, using Simbad. Simbad is very interactive. It gives data in different formats. Also, the tools are there to analyze the data. Also, the statistics packages are there inside the data. So, to begin research work, this is very interactive. Simbad package, Simbad database center is very interactive. So, what I recommend is first to go through the Simbad regarding the data, and then move to the NASA IPAC database. This is relatively not easy. There are softwares, but there are tutorials, but to handle data from NASA IPAC, it's you have to be used to. So this is just the first phase of if you just type this link, you see this page, and here you can see 5 columns: objects, data, literature, tools, and info. So first 3 is very important, and fourth is very, very important. You see, there are tools. You can have access to several softwares. You can download it freely. You can work offline using these softwares. You can see it here: coordinate transformation and extinction calculator, velocity calculator, cosmology calculator. A few students have used this cosmology calculator and modified its algorithm and run few important simulations, who completed master's thesis under my supervision. Now they are in Ohio University. They are doing PhD. Extinction law calculator. This is also very fascinating. It provides many options. Sky plot is there. XY offset to RA declination. There are several options as well. Also, you can also build. This is open interface, open source softwares. These are open source softwares. You can use these software even in Linux operating system, Apple. I used to use in Apple most of the time, and also in Windows. So this is interactive, independent of any operating system. You can see this is to get the data, to make a plan for the data. This is to get the data, even for the primary data. But you see, this is NASA extragalactic database. So this will provide database of galaxies other than our galaxies. Extragalactic means there are, there are trillions and trillion galaxies in the universe, trillions and trillion galaxies. And there are many other exotic objects outside our galaxies. So this provides database, mostly this NED provide database of extragalactic objects and processes. But Simbad provides galactic database, data of stars, data of pulsars, neutron stars, different types of Seyfert stars, blue Wolf-Rayet stars, and many kinds of stars, interstellar medium, dust and gas, and so on, many things covering all wavelengths. Simbad provides galactic data, and NED provides extragalactic data in principle. But there is an overlap between these two. You can have access to similar data using both huge database centers. So here is also literature, you can see it here. So this is also linked with ADS. So you can, if you want some literature immediately, if you are working using NAID, then you can go through this, but it has some limitations. You can or you can't download particular literature using this interface. But if you go to there is some copyright issue regarding NAID. NAID database maintaining center is quite expensive than others. So they may ask to charge money. They may, take care of this. As I said, tools are mostly free. You can also create your own tool and add it here. And you can also earn money if you do something new, something important for others. If someone use your tool, then you will get benefited. You will get some amount, okay? And additional information regarding these stuffs are given here. This is important for the future or any new news. All the time, whatever you do, you have to opt scientific, you have to opt some sort of scientific process to get something new, to get your findings so that you can publish your result in international journals. So there is a very simple scheme. First, you have to observe an event. You have to identify what sort of event you are interested in. So observe an event. So that event will give you a sets of database. You can have a huge set of database or a small set, medium range set. So you need one particular, you need to observe an event. Okay, and then what you have to do is you have observed one event. So you have to think on your observation. You have to look at, you should look at on the database. And you have to think on those data. You looked at you observe an event with your some say preliminary idea. Now you have a data. Now look at data and develop a model, predict something. Before analyzing data, you have not analyzed data. Just at the you have just looked at data and you develop a model because you have observed. For example, if you are interested in pulsar, or if you have observed one particular pulsar, then what I believe is you know what is pulsar, and you know properties of pulsar. You know what sort of things, what sort of unsolved issues regarding the pulsar, and you have observed one pulsar, so probably you know what is that pulsar, what is its position, what is its properties, how many people already looked at pulsar, how many literatures are there. So you have some background in your brain before the observation. So you have some observation. So you have background. So put it in that observation and develop a model. Okay. This is your preliminary hypothesis, which makes a prediction. This is just your prediction. This is very important. I usually say to my student, if you don't have any predictions, don't do research work. So you have to think, do not ask me. You have to put your own prediction. And then what you do is you test the prediction. You have put some predictions here. Now you need to test the predictions, whether your prediction is correct or not. Okay? If you test, this means you are doing something with your predictions. You are applying statistics, you are making plots, or you are making algorithm for the simulation, you are generating data, more data to add with that data. So test the predictions. Okay, if you test your prediction, you will have a result. You get something. If you test something, if you have a data, if you do something, you will have a result. Observe the result. Whatever you do, you observe the result, and then analyze that result. Revise and then what you get is your hypothesis is not correct. You found it. do something, and if you observe, if you get result and you observe your result, and then you intend to, this process compel you to revise your hypothesis. Okay, so repeat this as needed. You have to test your prediction 100 times by different methods, different tools. If you are very precise, if you have research experience of say 10 years, then you will be precise. You can have, with the help of your experience, past experience, probably you need to have 10 or 12 tests to verify or to revise your hypothesis. So you have to test the predictions, observe the result that you obtained from that test, revise the hypothesis as per needed, and repeat this test as needed. Okay, and you all know a successful hypothesis becomes a scientific theory. So what you do is, what you are going to do, what I suggest is develop a model or hypothesis and make it successful. If you make it successful with the help of data and model, what you do, you are creating something that is original thing, that is a new thing, that will be definitely published in international journals. So they should be very compatible with your testing mechanism and the model. So you are testing, you are putting one hypothesis. Based on that hypothesis, you have a model, and you are testing that model with the help of your data and several other methods. Okay, so this should be compatible, very compatible. Okay, uh, I should say thank you. I stop here for now because I have just given an exposure how to get literature, how to create interest, and how to go through the literature, and how to get data, and what sort of performance can be done with the data. So if you go to, I have just gone through 2 or 3 links. I haven't gone through the virtual sky observatory. I haven't gone through the archive because of some limitations of time as well. It's already 11:40 and I have another class at 12. Okay, I stop here. Thank you very much.
Thank you very much, sir, for your valuable time. We have, I can see that there are a few questions, 15 questions, but those questions are repeated and section wise. So I would ask, there is one interesting question I would like to take. Is there, I will ask, is there any opportunity to IT student in astronomy, maybe in data analysis? I am BCA student and don't have knowledge in physics. So is there any advice from our side, sir, to him, her?
I think you will be very important for a group of, you will collaborate with a project with the people, I think, because independently it's very difficult to do something new, because all these things will give a physical process to understand those process, but you will be very handy, very important to process the data, to perform with the algorithm, revise the algorithm as per needed. And if you explore your interest in particular area, you don't need to study more. If you are fascinated towards, for example, say, dark matter, and if you just try to read what is dark matter and what sort of data is available regarding dark matter, you need a little bit background. That's true. And you can collaborate with the people, with physics people who understand physics, and you will be co-author or you will be first author. But first author should have fundamental knowledge of hypothesis that relates natural process. So thank you.
Thank
Other
you, sir. So we
questions?
have,
Other question?
yeah,
Other specific question, please.
yeah, we have two questions I would like to merge from Jivan Shrestha and Dipsa Buratoki. Jivan writes, how can we introduce projects related to astronomy in high school? And Dipsa says, good morning. What can be done to attract youths in the field of astrophysics? So
What can be?
what can be done to attract youths in the field of astrophysics?
Okay. You see, astronomy is very difficult to attract because sky is always fascinating for even for children. So you don't need to do extra effort to motivate in this particular field. Even to the layman, you can motivate layman. You can also, if you make a very big group, I think, if you make a very big group, including layman, including some semi-skilled persons, including a physics student, and if you divide your work, even through very small telescope, new science can be done with very small telescopes. So even from the school, led by a school teacher, one can handle such things. So for astronomy, I think it's a very easy to motivate. You need a certain campaign, night sky observation campaign, so that people can be motivated towards the star, towards sky, why they are, why the things they are, what are the things that need to be understand, and so on. So this is interesting. One should do this, but unfortunately, in our school curriculum, this is not a provision. I studied in Europe during my PhD. I was there. So what I found is even school children, they use astrolabes, even very small, 6 or 7 years children, they use astrolabes, different astrolabes from their home, look at the sky, look at the constellations, try to identify constellations, and try to identify groups of the star, Pleiades or pole stars or many other groups of stars. So they are, so unfortunately our curriculum is very radical. So this is because of the, not only at the school level, also in the university level, our curriculum is curriculum for knowledge. And this is the time we need curriculum for skill or curriculum for invention. Okay, thank you.
Okay, we have another question, long questions. I think I allow this participant to speak himself.
Okay.
Nimesh, could you please ask your questions on your own? Nimesh?
Hello?
Yeah, please go ahead.
Please.
Sir, namaskar.
Namaste.
Can I ask the question in Nepali or should I have to do that in English?
Yeah, any language you can use. Okay. Any language means, of course, not Chinese. Yeah.
Okay.
Yeah.
Sir, म चाहिँ मेची बहुमुखी क्याम्पसमा BSc 4th इयर फिजिक्समा अध्ययनरत विद्यार्थी हुँ हैन र मैले 4 वर्ष BSc अध्ययन गर्ने क्रममा हाम्रो यो BSc सिस्टममा चाहिँ एउटा कुरिकुलममा एउटा मेजर फ्ल चाहिँ भेटे। यो चाहिँ खासै 2 वर्षदेखि मात्र आएको छ, किनभने म्याथमेटिक्समा पढाइ हुने कुरिकुलमलाई चाहिँ 4th इयरबाट जुन कम्प्युटर प्रोग्रामिङ 4th इयरमा पढाइ हुन्थ्यो त्यसलाई चाहिँ 3rd इयरमा खसाइयो र त्यसपछि यो एउटा एकदम मलाई लाग्छ एकदम एउटा इन्कन्सिस्टेन्सी जस्तो हो हैन। यो चाहिँ हाम्रो अहिलेको BSc को कुरिकुलम स्ट्रक्चरमा छ। म तपाईलाई यस बारेमा थोरै प्रश्न पार्छु। BSc 3rd इयरमा अहिले म्याथ 301 अन्तर्गत कम्प्युटर प्रोग्रामिङ विषय पढाइ हुन्छ र BSc 4th इयरमा चाहिँ कम्प्युटर फन्डामेन्टल्स पढाइ हुन्छ। अब समस्या के छ भने कम्प्युटर फन्डामेन्टल्स चाहिँ खास भन्नुपर्दा एउटा प्रिकर्सर जस्तो हो कम्प्युटर प्रोग्रामिङको लागि, किनभने तपाईलाई जब कम्प्युटर थाहा हुन्छ तब त्यसमा प्रोग्राम लेख्न ओर्न पोसाउँछ। प्लस कति फर्स्ट युनिट जुन छ हाम्रो कम्प्युटर प्रोग्रामिङमा पनि जुन चाहिँ पुरै हाम्रो 4th इयरमा पढाइ हुने कम्प्युटर फन्डामेन्टल्ससँग ओभरल्याप गर्छ र यो के हदसम्म यो ब्याकवर्ड छ हैन। जुन चाहिँ कम्प्युटर फन्डामेन्टल्स अगाडि हुनुपर्ने, कम्प्युटर प्रोग्रामिङ पछाडि हुनुपर्ने हैन। यो विषयमा तपाईको ध्यान आकर्षण भएको छ?
ओके, यो क्वेसन चाहिँ हामीले धेरै पहिलेदेखि थाहा भएको कुरा। अहिलेको डिसिप्लिन, अहिलेको सिस्टम कस्तो छ भने यो सिंगल लाइन एजुकेसन छैन कि बीएससी मा दुईटा डिसिप्लिन छ, फिजिकल ग्रुप बायोलोजिकल ग्रुप भनेर हैन। त्यसमा फिजिक्स पढ्ने स्टुडेन्टहरु फर्स्ट इयरमै फिजिक्स पढ्छु भनेर आउने स्टुडेन्टहरुलाई फिजिक्सको लागि मात्रै चाहिने स्ट्रिम चाहिँ गयो भने है, त्यसरी गयो भने फिजिक्स फर्स्ट इयर, यहाँ त थर्ड इयरमा गइसकेपछि मात्रै अब म फिजिक्स पढ्छु अथवा यो पढ्छु, थर्ड पनि होइन कि फोर्थमा गएपछि यु हेभ टु अप्सन्स when you are in third year. If you go to fourth year मा गइसकेपछि मात्रै हामी प्रिसाइज हुन्छौँ नि त है। हाम्रो 2 टायर सिस्टम छ। त्यसो हुँदाखेरि के भइदियो भने सबै विषयहरुको आफ्नो आफ्नो इन्ट्रेस्ट अनुसारले त्यो कोर्स चाहिँ फिजिकल ग्रुपलाई फिट हुने खालको कोर्स हालेर गयो। दिस इज भेरी रङ। यो अहिलेको कन्डिसनमा चाहिँ यो पुललाई हटाउनै पर्छ। फिजिकल ग्रुपले वर्क गर्दैन। फिजिक्स हामीले करिकुलम बनाएको थियौं 2013 मा बीएससी को लागि सेमेस्टर सिस्टमको। इट हैज 8 सेमेस्टर्स र फर्स्ट सेमेस्टरबाट नै फिजिक्स स्टुडेन्ट भनेर इनरोल हुन्छ उ र उले फर्स्ट सेकेन्ड थर्ड फोर्थ सेमेस्टरमा फिजिक्सलाई चाहिने कुराहरु म्याथमेटिक्सहरु चाहिन्छ, इभन स्ट्याटिस्टिक्स चाहिन्छ, हामीले फिक्स गर्छौं। फिजिक्स सब्जेक्ट कमिटीले फिक्स गर्छ फिजिक्सको लागि फिजिक्समा बीएससी कम्प्लिट गर्नलाई कुन कुन कुराहरु चाहिन्छ। त्यो कुराहरु मात्रै पढ्न दिएर फिजिक्समा ब्याचलर गराए भने, त्यसो गराए भने ब्याचलर लेभलको 6 सेमेस्टर 7 सेमेस्टर 8 सेमेस्टरको क्वालिटी र त्यहाँको रिसर्चहरु अहिलेको मास्टर्स लेभल भन्दा बेटर हुन्छ। तर यो डिसिप्लिन जबसम्म चाहिँ कोल्याप्स हुँदैन नि, फिजिकल ग्रुप र बायोलोजिकल ग्रुप, अब म्याथमेटिक्स डिपार्टमेन्टले आफ्नो करिकुलम बनाउँछ, कम्प्युटर डिपार्टमेन्टले करिकुलममा फोर्थ सेमेस्टरमा लगेर राखिदियो। फिजिक्सले बनाएको होइन। फिजिक्सलाई त खाली ठाउँ दिएको छ। फर्स्ट इयरमा तिमी 150 नम्बरको कोर्स बनाऊ, सेकेन्ड इयरमा 150 नम्बरको बनाऊ, थर्ड इयरमा आएर 300 नम्बरको यसरी पुलमा बनाऊ र फोर्थ इयरमा चाहिँ लिएर जाऊ आफ्नो है। त्यसैले दिस इज अ प्यारालाइज सिस्टम। आई शुड से दिस शुड बी रिवाइज्ड एज सुन एज पोसिबल। यो रिवाइज हुन्छ नै। यसपालि यो रिवाइज नहुनुको रिजन चाहिँ के, ठुल्ठुला कलेजहरु छन्, ठुल्ठुला कलेजहरुले त्यो कुरा एक्सेप्टै गरेका छैनन्। सेमेस्टर सिस्टममा जाने अथवा इभन एनुअल सिस्टममा गए पनि वान स्ट्रिम सिस्टममा जाने। फर्स्ट इयरमा हुँदा नै विद्यार्थीलाई थाहा हुनु पर्यो कि म अब के पढिरहेको छु, मेरो अल्टिमेट म कुन डिसिप्लिनमा मास्टर्स, ब्याचलरमा आइसकेपछि त प्रिसाइज हुनुपर्छ है। किनभने मेडिसिनमा जाँदा इन्जिनियरिङमा जाँदा चाहिँ प्रिसाइज भएर सुरुमै जाने है। अनि यतातिर जाँदाखेरि चाहिँ यसरी दुईटै ढुङ्गामा खुट्टा हालेर गयो भने त यस्तै खालको हुन्छ। केमिस्ट्रीले किन उसले म्याथमेटिक्सले के गर्यो, एनालिटिकल म्याथमेटिक्सले इलेक्टिभ पेपर आर्गुमेन्ट थियो, जबकि कम्प्युटरको कोर्स कम्प्युटर साइन्स डिपार्टमेन्टले फोर्थ इयरमा गरेर राख्यो, जुन चाहिँ एकदमै स्कुलमा पढेको कुरा हो। 9-10 मा पर्टिकुलर कलेजमा धेरै स्टुडेन्ट गएर हो, त्यो हामी सबैलाई थाहा छ। र त्यो कलेजले कहिले पनि तयार हुँदैन। कोटा सिस्टम अथवा अलिकति पछि त हुन्छ नै होला, किनभने स्टुडेन्ट if student realize these things, we are not in a very good packet. राम्रो प्याकेटमा बन्डल गरिएकै छैन स्टुडेन्टलाई पनि। स्टुडेन्टले त भिक्टिम स्टुडेन्ट भयो, स्टुडेन्टले त विद्रोह गर्नुपर्छ। ओके, थ्यांक यू।
हुन्छ सर। सो हजुर, अर्को एउटा क्वेशन हाम्रो युट्युब लाइभमा आयुष गौतम सोध्नुहुन्छ। उहाँ वीरेन्द्र टियु अन्डर ग्रेजुएट भनेर लेख्नु भएको छ। He said, sir, do you have any comments on research being done in computational astrophysics, numerical reality, or orbital simulations? So computational astrophysics, numerical reality, relativity, or orbital simulations.
There are several papers and several groups working on this particular area. धेरै जना काम गरिरहेका छन् computational reality मा अथवा कम्प्युटेशनल रिलेटिभिटीमा। पर्टिकुलरली कम्प्युटेशनल रिलेटिभिटी सुरुमा मात्रै होइन, अहिलेसम्म पनि कम्प्युटेसनबाट नै बढ्ता कुरा डिस्कस भइरहेछ। तर त्यो कम्प्युटेसनलाई हाई एनर्जी एस्ट्रोफिजिक्सले युज गर्छ, एस्ट्रो पार्टिकल फिजिक्स एक्सपेरिमेन्ट हुने ठाउँमा युज गर्छ। त्यो चाहे फर्मी ल्याबमा होस् अथवा एलएससीमा होस् है। सबभन्दा पहिले त कम्प्युटेसनबाट नै भर्चुअल एक्सपेरिमेन्ट गरेर टुङ्गो गरिन्छ, किनभने इट इज लेस कस्टली, थोरै पैसा खर्च हुन्छ। त्यसपछि मात्रै त्यो सक्सेस देखियो भने मात्रै एक्सपेरिमेन्टल परफर्म गरिन्छ। सो लार्ज नम्बर अफ सच कम्प्युटेशनल एक्टिभिटिज आर निडेड, particular considering relativistic aspect in astronomy. तर प्रब्लम के छ भने हामीले यहाँ गर्ने भनेको पीसीबाट हामी ल्यापटपबाट कम्पिटिसन गर्छौं भन्छौं नि, त्यो कम्पिटिसनै होइन त्यो। त्यसरी यो पीसी सीपीयूबाट सीपीयू को क्यापेसिटी नै हुँदैन लुपहरु बढ्ता बनाउने। You need to go to the GPU. You have at least 100 processors, or you should have a rack server. So हामी कहाँ छ केही ठाउँहरुमा जस्तै हामी सेन्ट्रल डिपार्टमेन्टमा हाम्रो 6 वटा र्याक सर्भर छ. It costs around 20 lakhs or so on. So कम्पिटिसन गर्ने भनेको डेटा क्याल्कुलेसन, डेटा एनालिसिसहरु गर्ने, प्लटिङहरु गर्ने र सानो सानो भिजुअलाइजेसन गर्ने ल्यापटपबाट गर्न सकिन्छ। तर मोडलिङ गर्ने, कम्पिटिसन गर्ने चाहिँ यो लिमिटेसन भन्दा स्पिड, यसको कम्पिटिसन स्पिड यसको पुग्दैन। Okay, thank you.
So we have another question. So I think this will be our second last question. So quickly, अलि लामै क्वेशन छ यो दाङबाट छ, म
हजुर
पार्टिसिपेन्टलाई सोध्न आग्रह गर्छु। हरि, प्लिज go ahead with your question. Hari Bhandari.
एउटा क्वेशन मैले देखे, does astrophysics includes space time? Yes, obviously. Relativity is a part of, without relativity, but that relativity is not say that relativity is not for a very huge massive particles, but for tiny particle relativistic limit is there inside the star. So we need this belongs to astrophysics, particularly in stellar astrophysics. Okay, question कसले read out गर्दै हुनुहुन्छ?
Hari Bhandari ji, please go ahead with your question. लामो भएको हुनाले उहाँलाई नै भन्नु।
मेरो क्वेशन के छ भने हाम्रो यो देशमा चाहिँ एस्ट्रोनोमीको बारेमा चाहिँ रिसर्च कम हुनुको कारण चाहिँ मेन पावरको कमीले हो कि या अथवा इकोनोमिक कन्डिसनको कारणले कम भएको सर, के होला सर यसमा रिसर्च कम हुनुको कारण?
इकोनोमिक कन्डिसन त यसमा चाहिँदैन, डेटाबेस फ्री छ र रिसर्च चाहिँ कम भएको र बढ्ता भएको भन्दा पनि रिसर्च कम भएको त म मान्दिनँ। यिनी जम्मा 100-150 जना स्टुडेन्टहरु मास्टर्स पढ्छन्। 100-150 जना स्टुडेन्टले हरेक वर्ष 50-60 जनाले मास्टर्समा एस्ट्रोफिजिक्समा थेसिस लेख्छन् र हरेक वर्ष 10-15-20 जना एस्ट्रोफिजिक्समै फर्दर स्टडी गर्नलाई जान्छन् है। So there are many people, they are doing research in astrophysics compared with other disciplines of physics. स्टुडेन्ट नै हेर्ने हो भने एस्ट्रोफिजिक्स अथवा स्पेस साइन्स बीएससी मा त मैले लास्ट इयरको डेटा हेर्दाखेरि यो म्याथ स्पेस साइन्स लिने अलमोस्ट 86% थिए नेपालमा बीएससी मा, 14% ले मात्रै ल्याछ। And they also perform lots of BSc projects in space science related projects, astrophysics related projects. About 44 BSc का स्टुडेन्टहरुले एज अ प्रोजेक्ट बीएससी प्रोजेक्टमा एउटा ब्याचले कम्प्लिट गरेको छ, थेसिस बुझाएको छ। त्यसमध्ये इन्ट्रेस्टिङ कुरा के छ भने 3 वटा स्टुडेन्टहरुले इन्टरनेशनल जर्नलमा पब्लिश गरेका छन्। This is an amazing achievement, not by other field. BSc लेभलमा इन्टरनेशनल लेभलमा पब्लिश भएको फिजिक्सको अरु फिल्डमा रिसर्च गरेकोहरुको छैन मेरो नोटिसमा। So there are lots of people are doing this thing, but you see astronomy भन्ने बित्तिकै जसले पनि रिसर्च गर्न सक्छ भन्ने होइन। You need a very hard stuff. हो हामीलाई के धेरैहरुले यो प्रोफेसनल टाइपको एस्ट्रोनोमी गरेर इन्ट्रेस्ट क्रिएट गरिन्छ र त्यसबाट स्मल टेलिस्कोप युज गरेर त्यसमा एड गरिदियो भने, भ्यालु एड गरिदियो भने, स्मल टेलिस्कोपबाट कन्टिन्युअस एफर्ट गरेर काम गरे भने न्यू साइन्सहरु गर्न सकिन्छ। प्रोफेसनल एस्ट्रोनोमीबाट पनि संसारभरि धेरै कुराहरु थाहा भएको छ त्यसबाट है। त्यसमा इन्भल्भ गराउनको लागि कोसिस गरिरहेछ नासाले, त्यो कुरा धेरै कोसिस गरिरहेछ। आई रियली एप्रिसिएट दिस रिगार्डिङ एस्टेरोइड और मेनी अदर सच अब्जेक्ट्स। इभन नेकेड आईले अब्जर्भ गरेर पनि रिसर्च हुन्छ। नाङ्गो आँखाले मात्रै कन्टिन्युअस हामी हेरौं त हामी प्लान गरेर नाङ्गो आँखाले हरेक इभिनिङमा तर राम्रो ठाउँमा जानु पर्यो क्लाउड क्लियर 1 वर्षमा 3 महिना त क्लाउड क्लियर होला त्यस्तो हामी 4-5 वर्ष कन्टिन्यू कुनै ग्रुपले रिसर्च गरोस् त कुनै एउटा स्टेलर ग्रुपमा र केही म्याग्निट्युडहरु क्याल्कुलेट गरेर थोरै स्पानको पनि थोरै पिरियडको पनि कलर म्याग्निट्युड डायग्राम बनाओस् त नेकेड आइले हेरेर त्यो पनि पब्लिश हुन्छ राम्रो जर्नलमा You see, Tycho Brahe was, you probably you know, Tycho Brahe ले 44 वर्षसम्म रातभरि हेरिरह्यो है उ राति त उसको कहिले पनि डे टाइम कहिले पनि रातिमा सुतेन उनले कन्टिन्यू होल लाइफमा 44 इयर्समा राति हेर्यो त्यो प्यासन चाहिँ भइदियो भने हामीले स्काई हेर्दाखेरि हामी कति मिनेटलाई हेर्छौं हामी गएर बाहिर क्लियर स्काई छ भने हामी 1 मिनेट 2 मिनेट 5 मिनेट 10 मिनेट हेरौँला है बाहिर गएर बरन्डामा गएर त I should compel you to go to concentrate at the sky and look at for about half an hour 1 hour even 2 hours just focus on try to आँखा पनि त टेलिस्कोप हो आँखालाई हामी धेरै फोटोन कलेक्ट गरौँ न आइमा त्यही एउटा स्टारलाई मात्रै हेरौँ त आधा घण्टासम्म त्यो स्टारको कलर देखिन्छ you can feel the color you can see the color whether that star is orange star or that star is lightest green star you need to collect more photon in your telescope in your eye so you need to have a great patience telescope sama pani त्यही हो you should have a great passion and you should have a tug and war with climate also कहिले बादल त्यो सट्ट जाला हामी अब्जर्भेटरीमा बस्दाखेरि च्यालेन्ज जस्तो हुन्थ्यो बादललाई त्यसले यो पुच्छरबाट छोड्ने बित्तिकै हामी अब्जर्भ गरिहाल्छौं त्यहाँबाट भन्नु it's a challenge you have to be very handy with those environment हामीले त प्रयोग गर्नुपर्छ है कहिलेकाहीँ बादल क्लाउड फेभरेबल भइदिन्छ उले फोटोनलाई डिरेक्सनल चेन्ज गराइदिन्छ हामीलाई बेनिफिट हामीले 1 घण्टासम्म कलेक्ट गरेर पाउने डेटालाई उले चाहिँ 45 मिनेट 45 मिनेटमै दिदिन्छ कहिलेकाहीँ बादलले त्यस्तो खालको ट्र्याकिङ गर्दिन्छ you need to optimize your condition even with the help of naked eye you can do original work but you need to have a patience for years and years okay
so there are I think can we take a last question sir if you allow
yeah please 12 बजे मैले अर्को पेजमा जानु पर्छ त्यहाँ
यो एउटा चाहिँ last questions I think there are also good memories of you working at observatories so do you recall any moments that working at the world's coolest places like observatories during your PhD and postdoc
yeah there are many but the problem is salary is very high problem के छ भने अब्जर्भेटरीमा बस त्यहाँ काम गर्नलाई धेरै समयसम्म मान्छे रुचाउँदैनन् है किनभने त्यो एकदमै आइसोलेटेड हुन्छ सिटीबाट पर हुन्छ एकदमै माथि हुन्छ त्यहाँनिर मोबाइलहरु अफ गरिया हुन्छ त्यहाँ हामीले हाम्रो कुनै पनि इलेक्ट्रोम्याग्नेटिक रेडिएसन इमिट गर्ने अब्जेक्टहरु बोक्न पाइदैन राति अब्जर्भेसनको टाइममा है अनि इभन अन्डरग्राउन्ड एरिया हुन्छ है यो नोइजलाई कन्ट्रोल गर्नको लागि धेरै स्टप गरे हुन्छ त्यहाँ so you need to be patient you need to be isolate from your family त्यस्तो खालको देखिन्छ you have a very good very attractive salary for example मैले पोस्टडक गरेको पिरियडमा जुन बेला म मर्नकियामा जान्थे त्यो बेलामा 1 month को मेरो स्यालेरी हुन्छ $8,000 हुन्थ्यो है this was the basic salary for postdoc मेरो अर्को कलिगले सिनियर कलिगले $13,000 पाउँथ्यो मेरो एउटा अर्को कलिग थिए इटालीको पीएचडी गर्दा पनि हामी सँगै थियौं एउटै इन्स्टिट्युटमा जियोभाना टेम्पोरिन भन्ने ही इज अ भेरी मैले के पाएको छु भने ही इज अ भेरी ग्रेट एस्ट्रोनोमर ग्रेटै भन्छु म किनभने शी हैज वर्कड फर अबाउट 13 years इन अब्जर्भेटरी इन अस्ट्रेलिया इन पादुआ अब्जर्भेटरी अल्सो इन माउना केआ अब्जर्भेटरी किनभने यो हाम्रो बाइ नेचर फिमेलहरुको कन्सन्ट्रेट गर्ने पेशेन्स एकदमै ग्रेट हुन्छ र अब्जर्भेटरीमा हामी के देख्छौं भने अलमोस्ट 30 to 35% सम्म एक्टिभ रिसर्चरहरु टेक्निशियनहरु चाहिँ मेलहरु एस्टाब्लिश अबाउट द पर्सनल लाइफको प्रब्लम एक्जिस्ट गर्छ ओके So no one wants to stay in the observatory for long. 1 year, 2 years को काम गरिसकेपछि वाक्क हुन्छ त्यहाँबाट जेनरली है। त्यसपछि ऊ युनिभर्सिटीमा बरु $1,200 को स्यालेरीमा आउँछ। त्यहाँनिर उसको नाइट लाइफ हुन्छ, सक्सेस लाइफ हुन्छ, उसको सबै सर्कल एक्टिभ हुन्छ। तर अब्जर्भेटरीमा त यु शुड बी passionate with your work.
Kind of,
This is a very challenging, very difficult thing. I should say they are heroes. Who looks,
it's like a great isolation, as we are doing
Yeah.
at this moment.
yeah, yeah, true, Suresh sir.
Thank you so much for your valuable time today. You have class at 12. We are already 5 minutes behind the schedule. Your class must be on. Thank you so much for your valuable time. There are some open questions which I'll try to answer. Maybe you can write something, answer them back.
Please send me.
And if anyone has some queries, please feel free to write. There will be one email coming to you tomorrow. So you can write at office@nepalaastronomicalsociety.org for any questions that we will be interested to forward to sir. And if there are similar kinds of questions like that, I can see that from the grade 11, 9, there are questions related to string theory, experimental astrophysics, how we can do, and there are also queries related how we can prepare ourselves. So on creating a foundation on astronomical understanding. So we'll be answering that. You can write, and we are also posting different links and information through our Facebook page, Instagram, LinkedIn, and website, of course. So please follow us and subscribe. Then you will be learning a lot. So with this note, let's thank our speaker for today, this morning, and our session will be over for today. Thank you.
Thanks for inviting me. You are doing a amazing job, particularly NASA. I should appreciate Mr. Suresh Bhattarai and his team for his continuous effort since last 10 or 12 years. I'm looking this. Thank you very much. Thank you. Thanks to all.
Thank you, sir. Thank you.
Okay, bye-bye. Namaste.
Bye-bye.